Welcome to Astro 101, the Sun and its Neighbors. I'm Professor Bart Netterfield. This lecture is the first of two covering the terrestrial planets, Mercury, Venus, Earth, and Mars. Now, first I want to do a quick review of some of the things we've already learned. If you recollect from the second lecture, we were looking at images like this of the solar system and how the planets all orbited around the sun. And in our covering of the Newton's laws and Kepler's laws, we can actually understand how this works. Gravity is causing the moving planets to go in closed circular orbits. The inner planets move the fastest because they have the strongest gravity because they're closest to the sun. And as they move out, the gravity becomes weaker, and therefore the planets move slower and slower. We also noticed in the second lecture that all of the planets are actually orbiting in a plane. When we look at the plane from the side, we'll see what we're talking about here. All the planets are orbiting more or less in the same plane. And this is something that we really didn't understand, but said we eventually would. So as you, these are just the four terrestrial planets we've been looking at here. These terrestrial planets, if you recall, are made of heavy materials, rock, metals. As you go further out from these, they have the terrestrial planets made of metals. As you go out past the Ceres and the other asteroids in the asteroid belt, you get to the planets like Jupiter and Saturn and Uranus and Neptune, and discover that these planets are much larger, much more massive, and made of lighter materials, gases and things that on Earth would be ices. So we want to understand how that works. And the way this works really comes down to our theory of planet formation. Now, I'm not going to give a full lecture on planet formation right now because that's been part of other lectures in the course that aren't recorded here, but I'm just going to give a quick summary. What happens is you start out with what's called a molecular cloud. This is a cloud of gas and dust in space. Now, the gas and the dust in these molecular clouds are the remnants from a previous generation of stars which has exploded. We'll cover that in Astro 201 in a lot more detail. But the idea here is you have a star, the star gets to the end of its life, the star explodes, throwing gas out into space, leaving a remnant, like a white dwarf or a neutron star or even a black hole. Most of the material gets blown off into the envelope, but a lot of it gets left behind in these remnants. And over time, there's less and less gas to work out. So in fact, the galaxy will eventually run out of gas and there'll be no more new stars. But that's not for quite a while, so don't panic quite yet. So anyway, we get these clouds of gas and dust. Gravity then begins to pull them together. Now these clouds of gas and dust are not completely uniform. There's lumps, there's more dense bits and there's less dense bits. And so gravity pulls the dense bits together. This is the law, like law of gravity in astrophysics. It's kind of like the rich get richer and the poor get poorer. So wherever there's stuff gets attracted. Where there isn't stuff, well, what it has gets even less. So these clouds are fracturing into lumps. Let's imagine one of these lumps, as it's collapsing, well, it had some angular momentum. It wasn't completely still, like I said. These clouds of gas were kind of moving around in different ways. And so this cloud that's clumping together to form a new star has some angular momentum. There's some net motion to it. It's not completely still. So as it shrinks, angular momentum causes it to start spinning faster and faster and faster. Kind of like, you know, the story with the figure skater. And when she brings her arms in, she causes her to spin faster and faster and faster. So the same thing's happening with this cloud. As it begins, it's, you know, at first you can't really tell it's moving, but as it collapses, it starts to spin faster and faster and faster. So now the cloud is spinning fairly fast. And because of that, in the direction of the spinning, it forms a disk because that acceleration as it spins keeps it from collapsing. Now it collapses in this direction, so you end up with a disk which is thin this way and fat that way. Now, as it continues to shrink and the spinning gets even bigger and it gets even thinner and denser, pretty soon particles that are not exactly in the disk, when they cross the disk, they collide with particles in the disk, and gradually the disk gets thinner and thinner and becomes a relatively thin disk, ending up with a spinning disk of gas and dust. In the core of it, you've got a star forming like the sun. Okay, so, well, what happens next? So you've got this disk of gas and dust, and some of the material in the disk can form solids, like little specks of dust, little chunks of dust. And those little chunks of dust can stick together, and they can be chemically bonded to each other. And now you have a bigger chunk of dust. And then gradually different pieces of dust hit that big piece of dust, and it gets bigger and bigger and bigger. And eventually 2 medium-sized chunks of dust stick together and form a big chunk of dust. And pretty soon the dust is continuing to stick together, becoming gravel, becoming rocks, and becoming very large rocks, and then planetesimals. Now, exactly how that process works isn't completely known. It's kind of exciting. There's lots of things in astrophysics we don't entirely know. But what I just said appears to be the general process, starting from gas and dust, them colliding together, sticking together, forming larger and larger chunks, to eventually you have planetesimals. Planetesimals are the seeds or the cores that will eventually become planets. When the planetesimal gets large enough, it starts to have gravity strong enough to attract other planetesimals to itself. And so small planetesimals become medium-sized ones become large ones, and eventually they become the planets. So that's the kind of scheme of how planet formation works. Starting with a giant cloud of gas and dust, the cloud of gas and dust collapses into smaller chunks. Those smaller chunks collapse to form stars and a disk around them. Material in the disk clumps together to form planetesimals and eventually planets. Okay, so that's great. But one of the big questions we had is, why are the inner planets made of rock and metal, and the outer planets are made of gas and ices, things that on Earth would be gases? So why is that? And why is Jupiter and Saturn, Uranus and Neptune all so much larger than Mercury, Venus, Earth, and Mars? So this is because of a thing called the frost line. So I've drawn the frost line. There's not actually a line in space. It kind of goes from, it's not a sharp line, but we're going to pretend it's a sharp line. Inside the, here's how it works. As you get closer to the sun, it gets hotter. Obviously, you're closer to the sun, it's hotter. As you get further from the sun, it gets colder. Well, I mean, that makes sense. Closer to the sun is hotter, further from the sun is cooler. Inside the frost line, the protoplanetary disk is made of about 2% metal, and the temperatures are low enough, below hundreds of degrees, so that the metal is a solid. Great. 0.2%. That's not very much. Then there's materials that form rock, about 0.4%. It's cool enough for rock to be solid. Well, yeah, it's below a few hundred degrees, so the rock is solid. Also, there's about 1.4% of other molecules, mostly hydrogen compounds, but also, for example, nitrogen gas, oxygen gas, things like that. Now, at the temperatures inside the frost line, these things are all gases. Think about methane. Methane is a gas inside the frost line. How about nitrogen? Nitrogen is a gas inside the frost line where it's warm enough. So on Earth, methane is natural gas. It's a gas. Now, if you take methane or nitrogen and cool it enough, it will become a solid. It becomes solid ice. But inside the frost line, these things are gases. The rest, about 98%, is helium and hydrogen, which is a gas at pretty much any temperature. It's going to be really hard to find a place where there's hydrogen and helium gas, which is also cold enough that it's not a liquid. So this is different than what's happening outside the frost line. Outside the frost line, a lot of it's the same. You still have 0.2% metal, which is a solid because it's cold enough. Yes, it's really cold now. It's about 0.4 degrees rock, which is a solid. Of course, is really cold. And it's about 1.4% hydrogen compounds. And outside the frost line, it's cold enough for these to become solids. So methane is no longer a gas. It becomes a liquid or a solid. And many of these hydrogen compounds become solids outside the frost line. That's what the frost line is. Inside the frost line, these materials are gases. Outside the frost line, it's colder, so these materials are solids. And then you still have the 98% of hydrogen and helium gas. So what has this got to do with planet formation? Well, inside the frost line, only metal and rock can form planetesimals. All of that hydrogen compounds, which is like, more than twice as much as you have in metals and rocks, all of those hydrogen compounds can't be part of the part of the planetesimal formation process because they're gas. They can't stick together. They can't form rocks. Outside the frost line, however, they can. And so you have more than twice as much material outside the frost line that you can form to make planets. And so you expect the planets outside the frost line to be able to grow larger because you have a lot more material that they can form into. And secondly, because they get bigger, then their gravity can be strong enough that they can also start to attract hydrogen and helium gas. So Jupiter is so large because while it has a core of, or the inner surface, we'll talk about more at the core later, but the inner part of Jupiter is metal and rock and hydrogen compounds, the gravity of which was strong enough to attract all of the other materials onto it. So you have this giant planet. And that's a similar story with Saturn. But we're talking about inside the frost line. Inside the frost line, all you can do is make your planets out of metal and rock. You can't make it out of hydrogen compounds, and you can't make it out of hydrogen and helium because it's simply, there's not enough material. So tiny objects stick together to form planetesimals, and these are the seeds, or the cores will become planets. The planetesimals stick together and eventually form the terrestrial planets. So next, let's do an instant quiz, just so we can make sure we're following what we're doing so far. Take this quiz question. Rhea is one of Saturn's moons. Based on where it was formed, its composition is probably what? Mostly rock with a metal core? Mostly ice, but also some rock and metal? Mostly metal with some ice on the surface? Or the composition doesn't depend on where it was formed? So based on what we talked about, talking about the frost line, talking about where Rhea is, which of these four do you think is right? Now let's reason it through. Rhea is one of Saturn's moons. Saturn is one of the Jovian planets, which exists outside the frost line. Now outside the frost line, what can you make planets out of? Well, metal, rock, and ice. So it's going to be made from metal, rock, and ice. What will it be mostly? Well, most of the material you can make it out of is ice. So we expect, just from where it was formed, that Rhea is mostly made of ices. And in fact, that is the case. So the answer for this instant quiz question is B. Rhea is mostly ice, but also with rock and metal. Okay, let's get on to the terrestrial planets. The four terrestrial planets are Mercury, Venus, Earth, Mars, and we're going to throw in Earth's moon. It's not really a terrestrial planet, but it's large enough that we're just going to include it in our discussion because it's actually going to be useful to talk about Earth's moon as compared to the other terrestrial planets. These planets are, as we learned in the second lecture, all small, rocky, made of rock and metal. They have relatively thin or no atmosphere. They have very few moons. In fact, the Earth has a very large moon. Mars has a couple insignificant moons. And Venus and Mercury don't have moons at all. And they're made from heavy elements, rock and metal. So another thing we notice, if we look at Mercury and the moon, if we look up close, we'll see that Mercury is actually covered in craters. So there's all these craters on the surface of Mercury, and there's all these craters on the surface of the moon. Mercury and the moon are covered with craters. There are various sizes. Some are very large. You can see here the edge of an extremely large crater. And there's like really tiny ones that go all the way down to the size you can barely see. They're overlapping. You can see that there's craters on top of each other. There's a medium-sized crater with craters inside the craters and two craters that are next to each other. It's like the craters are overlapping. And so we might ask ourselves, what are craters? I mean, we think we already know what craters are, but let's just go ahead and summarize what people think craters are. The idea is that a planetesimal strikes the surface. Boom. Its typical speed is around 100,000 kilometers an hour. It could be 50,000, but that's the ballpark. It's going extraordinarily fast. And it's going extraordinarily fast, and when it hits the planet, or the moon, all that energy gets converted into heat. And there's a giant explosion which vaporizes the rock. So you end up, instead of having rock, you have gaseous rock, and that explosion blows an enormous hole, leaving a crater. We know this to be true from the materials we see around craters. We know this to be true from simulations of craters and experiments involving craters and making fake craters on Earth. But So that's great. So we understand what craters are. Good. Not much else to say, but there's actually a little bit of a challenge here. There's just not enough planetesimals in the solar system to make as many craters as there are on the moon. We know the moon is only about 4.5 billion years old, and the rate of craters is nowhere near enough to make the number of craters as there are on the moon. And secondly, we see all these craters on the moon, we see all these craters on Mercury, but we don't see them on Earth, Mars, and Venus. So those are two questions we need to answer before we go on. We can answer the first one actually pretty easily. Remember, we were talking about planet formation. We had the dust particles sticking together to form gravel, and the gravel sticking together to form rocks and boulders and big boulders and tiny planetesimals and large planetesimals, and they build their way up. Now, during the early times, there was a lot more little bits of stuff. In fact, stuff is still sticking together. And so the craters that we see are from that early time, when the planets are mostly made, but the last chunks are kind of getting gathered into the planets. That's a period called the heavy bombardment. There were far more planetesimals right after the planets were formed, and so then there are the final stages of little rocks and gravel and planetesimals crashing into the planets. That's called the period called the heavy bombardment, and it ended about 4 billion years ago. So the first few hundred million years is made up of stuff sticking together, and finally, at the end of that, the last rain of rubble onto the planets. That was called the heavy bombardment, and since then it's been dropping and dropping and dropping. So the rate of cratering now is much, much, much lower than it was in the past. So that all makes sense. Like, we expect there to be far more craters on the moon and on Mercury than are being formed now because of this. Because we know in the past, when the planets were being assembled, there was lots of stuff raining down, and that just gradually dropped away. So great, we got that first problem answered. Now there's another question we're going to come up with, which is actually related to the question of why there's no craters on Venus and on Earth and on Mars, or very few craters. There's some. We'll get into that next lecture. So we saw that Mercury and the moon are covered with craters, all these craters, but not everywhere. There are spots on the moon called mares that basically don't have any. There's a few, but like here you have like all these craters, and then it's pretty smooth, and there's very few craters. Apparently, something happened here to erase the craters after the heavy bombardment. Like, our theory of the heavy bombardment is that you have these chunks falling everywhere. So the moon should be covered everywhere with craters if that was the only story. But apparently, there are some spots on the moon. In fact, all these dark spots here are called mares. And all these dark spots are places where something has erased the craters. And so we want to understand what could have erased the craters. Now, one thing you can think of is like, well, maybe volcanoes could erase the craters. But, I mean, we can't just say that. We want to try and explore, well, what's going on inside the Earth that could possibly cause volcanoes, or what's happening inside the moon or Mercury that could have caused volcanoes that could wipe this out. That's a huge volcano if we wipe all that out. So what we want to know is, can we look under the surface of a planet? Because if we can look under the surface of a planet, we can start to explore whether or not you could actually get, volcanic activity to the point where you could, get rid of craters. So how could we do it? Well, we could drill holes, right? So we're going to get a drill bit, and we're going to drill a hole deep into the Earth, go down and nick a core all the way to the center of the Earth and find out what the Earth is made of. No, we can't do that. The biggest drill hole ever made is 12 kilometers. Now, can you imagine a drill bit 12 kilometers long? I mean, it's absolutely stunning they could go that deep. But the Earth's radius is like, what, 6,400 kilometers, 6,371 kilometers. I mean, we barely scratched the surface with drill holes. So you can't really use drill holes to probe into the center of the Earth. Okay, maybe we can use X-rays, right? Like, you look inside a person with X-rays. Yeah, no, because X-rays don't penetrate rock. They do a little bit, but not feet, let alone thousands of kilometers. All right, how else can you look inside something? Ultrasound. Maybe we can use sound waves like ultrasound does, right? How's that sound? We'll use sound waves, and maybe some, put some ultrasound generator somewhere, and then, yes, in fact, that works. Okay, so let's think about this. Imagine you have an earthquake here. It's going to shake the Earth, and it's going to send sound waves traveling through the Earth. And they're going to travel different paths, and they're all going to show up. Well, they'll show up everywhere. If we put a seismometer here and ask all the waves that made it to the seismometer across the Earth, how did the sound waves get here? Some of them traveled deep and bent up. Some of them traveled off the surface and reflected. Some of them just traveled through the Earth's surface. By looking at the waves and the timing of the waves and when the waves arrive, you can actually probe what's inside the Earth. Now, what you're going to want to do is use lots of these earthquakes in lots of places. Okay, but fortunately, there's lots of earthquakes in lots of places, and we can put seismometers in lots of places. You can, for local stuff, you can even use thumpers that kind of vibrate the ground or things like this. So let's look at it more carefully. Turns out that earthquakes, when they happen, cause vibrations, sound waves, to travel through the Earth. There's two kinds. There's the P waves, which are compression waves. Those are legitimately what you would think of as sound waves. That's imagine here a slinky, and you're shaking the slinky, and you get these density pulses traveling through the slinky. Those density pulses are P waves. There's also S waves, which are traveling up and down. So imagine shaking the slinky and having the waves go up and down. So the same thing can happen as you send a wave through the rock. You can have compression waves, just sound traveling through the rock, or you could have it so you've shaken the rock up and down, and then you have the rock shaking sideways as it goes through the Earth. So S waves and P waves. And S waves and P waves behave quite differently as they travel through the Earth. Let's first talk about the S waves. So the S waves are these up and down waves. S waves, let's see, you have a source of seismic waves here, and the waves travel out in all directions. And so if you put a seismometer here, a little after the earthquake, you'll see the wave hit it. If you had a seismometer here, a little while later, you'll see it hit it. Now, so the timing for the seismometers at different places depends on how far and how fast the wave has traveled. If it's traveled a long distance, it's going to be a big delay. If it's a short distance, it'll be a short delay. If it's taken a circuitous route, like it's bent rather than coming straight, the timing will be different. Okay. Also, it turns out that these S waves can't go through liquid. And we see there's a shadow from here to here, where seismometers see no S waves. So that's pretty good evidence that there must be a liquid core down inside the Earth. And by the size of it, it's going from here to here, by the size of it, you can tell how big the liquid core must be. So we know the Earth has a liquid core, and we know how large it is. Well, that's pretty cool. So we actually can probe down inside the Earth and discover there's a core of liquid. Secondly, liquid stuff, S waves, there must be a liquid layer in the core. P waves are different. P waves can go through liquid. So same story, timing for seismometers in different places depends on how far and how fast the waves traveled. But also, when they go through a change in density, they're going to bend. So we have this gap from 103 to 150 on Earth, where you don't see any P waves coming from a earthquake across the Earth. Back here on the opposite side, you do see them showing up. Here we do see them showing up, but in this little shadow here we don't. Now that's going to be because we know there's a density change. If we could see them here, we would know there was no sharp density change. But because we have the shadow here, we know there's a sharp density change, which causes the waves to bend. So we know the core is denser than the area above it. So we know there's a dense core in the middle, and we know that the dense core is, at least the outer part of it, is liquid. That's pretty cool. So there must be layers. So just to summarize the situation, we have seismometers we place all around the Earth. There's an earthquake. We look at the S waves and the P waves based on the timing. So we have the P waves coming first, and then later we see the S waves coming. You can tell they're S waves versus P waves by whether or not they're vertical or horizontal. So the vertical ones in this case are P waves, and the horizontal ones are S waves. By combining seismometers around the Earth and looking at many, many earthquakes, you can eventually begin to build up a fairly complete picture of what the interior of the Earth looks like. And so this is kind of the picture we've got. We've got the Earth. It's got a hot, solid inner core, a liquid outer core, and then a mantle made of hot rock. You also have the Moon and Mars. Mars has a core, probably, but a cool mantle, and Mercury has a core and a cool mantle. These planets have been measured with this is Mars, yes. They've been measured by seismometers. Places where we've landed spacecraft. We've landed spacecraft on Earth, obviously, and so we can place seismometers on Earth. We've landed spacecraft on the Moon. So when almost every one of the landing spacecraft that's gone to the Moon has included a seismometer for this purpose. And the first thing you find out is that there's very few earthquakes on the Moon, like none-ish. So what they do instead is they crash things onto the Moon. So they'll take the booster stage and crash it onto the Moon. That makes up a thump, and then they measure what's going on with the seismometers from all of the spacecraft that have landed on the Moon, and they've been able to put together a picture of the Moon. There appears to be a solid core, not a liquid core. So you've got that ring shadow, but not the full shadow. So it's not a liquid core, it's a solid core. It's fairly small on the Moon. Mars, similarly, they've landed a number of spacecraft on Mars and been able to start to look at seismic activity there to try and get an idea of what the interior of Mars looks like. And again, Earth has this solid inner core, a hot liquid outer core, and then a mantle that is hot, and then a crust on top. Mercury appears to have a partial liquid core and then a cool mantle. That's been measured from density and spin rate variations. Obviously, we've never been able to land anything on Mercury. It's incredibly hard to land on Mercury. We'll try and cover that later. Why that it's so hard to land on Mercury? Basically, because how do you slow down? Because you've gone in toward the sun. You have to speed up a lot. You're going to speed up a lot because of gravity. And now how do you slow down enough to actually land on on Mercury? It's really hard. Venus, so it's only been, nothing's ever landed there, but we've been able to estimate what the core is like because of the density and the spin rate variations. And then Venus, it's mostly a guess what's going on inside Venus. It's mostly estimated from density. We know how dense it is, therefore we kind of know there must be some kind of metal heavy core to make it actually have the right density, but it's really tough. So what about these layers? The crust is low density rock. That's the kind of rock we see on Earth, stuff that mountains are made of and like the rock around us. It's relatively low density rock. Then you have the mantle, which is medium density rock. The low density rock is kind of floated to the top, and the medium density rock is in the middle. And the core is the highest density, made from iron and nickel. And it makes sense that the core is the heaviest because it's going to sink to the center while the other things float up. So this is our picture of what's going on inside the Earth. The core is extremely hot and it cools as it comes out. So why do planets have cores? And why is there a crust? Well, lighter material. So imagine early on in the Earth formation process when it's very, very hot because it's assembling together and have all these explosions going on. The whole Earth is very, very hot enough to be all liquid. In that case, you expect the dense materials to sink to the bottom, with the lighter materials float to the top. So this is what's called differentiation. The lightest material becomes the crust rock on the surface. The mantle is the medium density stuff, and the core is nickel and iron, the heaviest metals, sinking to the core. So that makes sense, and it matches what we see with the seismometers. So that's good. That's exciting. Okay, so we know why the planets are differentiated, why there's a solid core and a lower density mantle. But the other thing we notice is that the cores are hot and the surfaces are cooler. So we have to understand why that is and how we can understand the temperature gradients. We also see that like Mars and the Moon and Mercury are a lot cooler on the surface than, say, the Earth. And we don't really know what's going on with Venus. We're just kind of guessing, but we'll assume it's probably very similar to the Earth. So the question we have to ask is, why are planet interiors so hot? Well, the first reason is what's called accretion. The idea here is, as you're assembling a planet, as things are smashing down onto it, those collisions create a lot of energy. All of that energy from speed, from gravity, gets converted into heat when it collides with the planet. And that process just warms up the rock. It just keeps, and when it's happening rapidly, when there's a lot of accretion going on, then it's going to heat up the planet so much that the planet will become basically all liquid. You end up with this lava planet where it's just all liquid rock and metal, and that's from accretion. And that's dominant during planet formation, where these collisions are happening kind of continuously. They're very, very hot. Okay, so after the accretion has started to slow down, the next thing kind of takes over, and that's called differentiation. While it's still hot, so this is happening during accretion, but then accretion ends and this will continue. You have the heavy materials sinking to the core and lighter materials floating to the surface. And as they move past each other, that actually, from friction, converts gravitational potential energy into heat. And so this motion, the sinking of the heavy materials and the floating of the light materials, that differentiation will serve to warm up the mantle. So that's the second source of heat. And the third source is that there actually is, within the Earth, radioactive materials like uranium from the formation of the solar system, remnants from a previous supernova explosion or a previous neutron star collision or something like that. These radioactive materials, which fill the Earth, are gradually decaying, undergoing radioactive decay, kind of like a nuclear reaction. It is a nuclear reaction. So it's like there's a super low power, huge reactor inside the Earth. Very, very slowly, over billions of years, the uranium decaying down into lead and other materials, which serves to at a very low level, keep the interior of the Earth warm. So that is the dominant source of heating inside the Earth today, is radioactive decay. That gradually decreases, but that's what's happening. So that's why the interiors are hot. So why doesn't it just stay hot? Why wouldn't it just stay, okay, well, it was thousands of degrees in the past. Why wouldn't it just stay there forever? Well, the planets do also cool. But we want to look at, how do they cool? What are the processes that cause a planet to cool? The first stage, the most important stage for getting heat from the core up to the crust, is a process called convection. Turns out that the mantle, even now, even though it's cool, the mantle is not completely rigid. It's kind of like really, really thick taffy, but really, really, really thick taffy. Almost like you can slowly bend the rock and it doesn't break type taffy. The planet's mantle is not completely rigid. It turns out that hot rock, or hot mantle material, weighs less than cooler rock. So what happens is that the hot rock rises. It kind of floats up and cools, and then it sinks, and you get these convection cells. Now, I don't know if you've ever boiled water in a clear glass kettle. You can see that sort of thing happening, where the hot air from the hot liquid from the bottom is rising up, and the cold liquid from the top is sinking, and you get this kind of moving of the liquid. That's happening on Earth, except because of the density and the viscosity of the rock, the little loops are really big. They're hundreds of thousands of miles across. So you get this convection happening. Hot rock rising, cold rock sinking, bringing the heat from the core up to the crust. That's step one. Step two, conduction. Now the crust is colder and more brittle and doesn't undergo convection. It's just too cold for it. If you tried to do that, it would just crack. So the surface doesn't move. So you get heat through it just through conduction, right? If you heat up one end of a thing, the other end of the thing will eventually heat up. It's slow, but it does happen. So that is a stage of taking the hot mantle and letting the heat leak through the crust, which actually does act like a pretty good blanket. The crust, because it's this relatively low density rock, it's not a great thermal conductor. So it's slow. It kind of keeps the interior kind of warm, but the heat does leak through the crust and eventually get to the surface. the last stage is radiation. Now, so radiation, anything that's warm glows with what's called black body radiation. If you don't know what that is, don't worry about it. But basically, anything that's warm glows. Now, it may not be invisible light. Things that are like my temperature or your temperature will glow with what's called infrared light. Your eyes can't see it, but it's still heat, it's still light. And that's how the surface cools. It sends light off into space. Now, there's also light coming from the sun and hitting the Earth. And so you end up with a trade-off. You have light leaving, you have infrared light leaving, and you have visible light and infrared light coming in from the sun and hitting the Earth. And there's a balance. And if there's more light from the sun hitting the Earth than there is heat from the core trying to leave, then the Earth will warm up. If, on the other hand, there's more light trying to leave than there is sunlight coming to the Earth, it's going to cool down. So we're going to be looking at that kind of thing in a couple of lectures when we start talking about greenhouse gases and such. So, but right now, we're just thinking about a moonless planet, a gasless planet. The surface radiates into space. So those are the three methods for cooling. Use convection to bring heat up from the core to the crust. Then you have conduction through the crust. And finally, you have radiation out into space. So, well, what about the size of the planet? Does that matter? And the answer is, yes, it does. So the best way to understand it is through math. And I'm going to give you the equations for why this is true. And if your eyes glaze over, don't worry. We'll come back to comprehensible stuff in a second. But if you find that math actually, the reality is some things are much easier to understand with math. If you just relax, understand the equation, it becomes a lot easier to think about. So I'm going to use math to explain it. We'll see how we go. So it turns out, if we think about the volume of a sphere, you may have learned this back in high school. The volume of a sphere is 4/3 pi r cubed. So it's the radius times the radius times the radius. That's what r cubed means. You take the radius times the radius times the radius. Then you multiply it by a number called pi, which is about 3.1415926 something or other. And then multiply that by 4/3. That gives you the volume of the sphere. So what that means is that if you double the radius of a sphere, the volume inside goes up by radius cubed by 2 times 2 times 2. You double the radius, then the volume increases by 8. The surface area of a sphere is 4 times pi, that same number, times the radius squared. So the area is 4 times pi times r squared. So if you double the radius, the volume is 8 times bigger, so 2 times 2 times 2. If you double the radius, the area is only 4 times bigger. So think about this whole cooling process. Eventually, all the cooling comes from radiation from the surface. The more surface you've got, the more heat you can get off. But the more volume you have, well, the more heat you have to get rid of. So if you have a planet which is twice as big, you're going to find that it's going to cool twice as slow, because the surface area to volume ratio is lower. So small planets have less mass compared to its surface area than large planets. So a small planet has less mass, less volume compared to its surface area than a large planet. And so small planets cool faster. And that's the thing you need to remember, because of how the way the volume and area works. You can put the rest aside. Because of the way of the ratio of volume and area, small things cool faster. And I think we already know that, right? Imagine you take out of the oven, after everything's hot and cooked, a large potato and a pea, and ask, which is going to cool faster? Well, you know, the pea is going to cool pretty fast, and the potato is going to take quite a while, because the surface area to volume ratio is much larger for a pea than for a potato. Okay, so the point is, small planets cool faster. We can see it through the math. We can also just know that from our life experience. Okay, let's do another instant quiz. Imagine that a planet and its much smaller moon start at the same temperature. After 1 billion years, which will be cooler? A, the planet, because it has a larger surface area to radiate from. The moon, because it has a greater surface area to volume ratio. C, they will be the same because they both radiate in the same way. Or D, it depends on whether they were formed outside the frost line. So go ahead and pause it for a second and see if you can, if you know the right answer. Hopefully you do. Okay, well, we just said smaller objects cool faster than larger objects. That means that the moon, which is smaller, will be cooler because it has a greater surface area to volume ratio. So we expect small things to cool faster than large things. So let's bring it back to this picture. We find that the small planets are cooler than the large planets because they've had a better chance to cool. We expect the coolest now, the least geologically active now, the one that cooled the quickest, to be the moon because it's the smallest. Then Mercury should have cooled the next speed up, then Mars, and then Venus and the Earth, which are very close to the same size. That would be what our expectation is, and that appears to be true, at least for these 3 planets, based on the seismological data. So that's good. The Earth, still hot inside. The moon, cold and dead. So let's go back to this question of, can we understand these mares, these parts of the moon where the craters were erased? Can we understand them? Well, we know that something must have happened after heavy bombardment, only on some parts of the moon, but then quit, because we still see some craters, right? So at some point it quit. It happened in the past and then was done. So I guess we can understand that now, right? Because early on in the moon's lifetime, the core was hot, and you could have liquid rock coming up out of the crust, and then later it cooled, and you can't anymore. So we basically get this kind of story. We started with a completely cratered surface. The whole of the moon was cratered. This is at the end. This is just after the end of heavy bombardment. It's like there's a few things still happening. You can still get a few random planetesimals hitting, and one did. You had some large impact come and damage the lithosphere. Smack. The lithosphere is another name for the crust. It somehow damaged the lithosphere. People aren't exactly sure how, but enough so that molten lava could leak up from the hot mantle underneath. And it turns out that liquid mantle is very viscous, very runny, non-viscous, very low viscosity. So it comes up and it just kind of makes a puddle and fills all the lowlands with this molten lava. And then it cools, and you end up with a large, smooth surface. There still are a few more impacts that happen after that, so you can still get a few craters, but mostly smooth compared to the rest. So that's what we think caused the mares on the moon. It's after the heavy bombardment, before the moon cooled enough. Now, there's a few things we don't really understand. One thing we see is that the mares are all in the size of the moon that face the Earth, and there's virtually none on the opposite side of the moon. We don't really know why. Well, maybe because something to do with tides, but that doesn't make sense because it affects both sides the same. Maybe we don't know. We don't know what the problem is. People are working on it. It's kind of cool that not all questions in physics are answered. And there's one that people are still working on. There's lots of ideas. It may be pretty quickly that something like, maybe it's to do with the fact that the Earth, I don't know. Who knows? Hopefully people will figure it out. But we think this is what's going on with the mares. In fact, when the Apollo missions landed there, they measured to make sure, yeah, that is in fact volcanic material that filled that in. So that we kind of know that's true. Exactly why it's only on the Earth-facing side and how the craters really could cause this damage isn't completely clear, but I think as time goes on, we're going to understand it. Anyway, okay, so that's cool. It turns out that there aren't mares only on the moon. You also see them on Mercury. You see these mares here where you have less volcanic activity than you have here, or something where it's kind of filled in. But the other thing that I noticed about Mercury is that it's less cratered than the moon. And does that make sense? Well, I guess we expect Mercury to cool slower. So is probably liquid enough, or had enough liquid underneath the surface enough to gradually wipe out the craters for a little bit longer than on the moon. So Mercury ends up very cratered, but not as cratered as the moon. So it all's kind of holding together with this: large objects cool slower than small objects. The moon cools first. It cools really at the end of heavy bombardment. Mercury maybe cooled a little bit later, and so the surface is a little bit less cratered because it had a chance for volcanic activity and stuff to wipe out some of the early craters. But it doesn't happen anymore. Both Mercury and the moon are geologically dead. All right, let's do another instant quiz. On this, you see this picture here. On this icy moon of Saturn, it's known as Enceladus, where has the surface changed more recently? Or where is the surface younger? So this area down here, I've called B, or this area up here, I've called A. And if you look here, look, what's the difference between these two parts of the surface? You see up here, what do you see? Lots of craters. That kind of tells us that, this part of these craters probably happened at the end of the heavy bombardment period. So you can have an idea of how old that part of the surface is. Down here, virtually no craters. Now, without asking yourself how it happened, it seems pretty clear. Well, I'll give you a second. Think about what the answer is. OK, let's get to the answer. The answer is B. There's virtually no craters down here, which means this surface, whatever caused this surface to be the way it is, it happened after the heavy bombardment. In fact, quite a bit after, because there's almost no craters down here. So this is a relatively young surface, where this is very, very old surface. How? Why? We're not answering that right now. We can just look at a surface and say, if you see a lot of cratering, it's probably older. If there's no cratering, then it's almost certainly younger. So we can just look at it. You can now look at a planet or a moon or something where you see lots of craters. That is old surface. Nothing's happened to it for the last 4 billion years. No craters, young surface. Something must have paved it over somehow, volcanic activity or something like that. We're not right now explaining what happened to Enceladus. I want to just look at the difference between the two. OK, so that's the end of this lecture. We've looked at how planet formation works, at what caused the interior planets to be made of rock and metals, whereas the outer planets, the Jovian planets, are made more of gas and ices. We've looked at how we can peer inside the Earth to see the various layers of the Earth and understand the heating and cooling of planets, to understand why larger planets may have more volcanic activity than smaller planets. We've looked at Mars and Mercury and what sort of processes affected their surfaces. And now we have the ability to look at the surface of anything and say, is this old or is this young? So I think it's been a pretty interesting lecture, and we'll be back for another lecture soon.